In lesson 5.4, we're going to look at analyzing binomial random variables. So to calculate the mean of a discrete random variable, we use this formula. And we use that calculator to help us do it when it was just a discrete random variable. But now that we're talking about a binomial random variable, it's even simpler. So notice the mu x, that means the mean of x, is n times p. Now, n is the number of trials that the problem gives us, and p is the probability of a success that the problem also gives us. So it's really simple to find the mean. Now, to calculate the standard deviation of the discrete random variable was this crazy formula, and we depended on the calculator to do that for us as well. But when we're talking about a binomial random variable, the formula is a little simpler. Notice it's still sigma x, and it's the square root of n times p times 1 minus p. N is still the number of trials, p is still the probability of a success, and 1 minus p is just 1 minus that probability. Now, these formulas are fabulous, but they are only for the mean and standard deviation for binomial distributions. You can't use them unless you know it's binomial and it fits the Venn criteria that we talked about. So according to the science of genetics, the genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Let x equal the number of children with type O blood. All right, so it is binomial. It passes the test because either the success is having type O blood, failure is not having it. I is one kid's genes is independent of the other. They told us that. N is number of trials, and they have 5 children. And S is the probability is the same each time, and it's 0.25. Okay, so we know it meets the criteria. And here's our distribution table. And based on the formula for the mean, n times p, n is 5, and trials is 0.25, and the mean is 1.25. All right, that's it. Standard deviation, remember, sigma x equals the square root of n times p times 1 minus p. So here's n, here's p, and 1 minus p is 1 minus 0.25, so that's 0.75, and that's where they got that right there in the formula. Okay, so you multiply those out, then take the square root, and you get 0.968. Really simple calculation. So let's try one of these. According to the same thing, science of genetics, the genes children receive from their parents are independent from one another. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. X is the number of children with type O blood. All right, so the question is, what's the probability that at most one of the children has type O blood? In symbol, it looks like this. The P, here it is. X is less than or equal to 1. This is an at most type of situation. We can compute this. This is called a cumulative binomial probability using this fact. Okay, using the fact that P of x is less than or equal to 1, that is the same as P is of x of 0 plus the probability that x is 1, right? Because these are the only two things. Now, it's pretty simple. If we use this table, we could do this. If we add them, we get 0.2373 plus 0.3955. And when I add them, I get 0.6328. Now, there is a way to do this, a cumulative thing, in the calculator, okay? And it looks like this. It says binomial CDF. Now, it's CDF, that C stands for cumulative distribution function, all right? Now, the CDF is always goes with a less than or equals to, okay? It always goes with a less than or equals to. It doesn't go with the greater than, and I'll show you what to do. So on the calculator, what you would do is you would go to second bars, like we did before, and you would not go to A, you would go to B, where it says binom CDF. The number of trials is 5, p-value is 0.25, and the x value is, what is it, less than 1, less than or equal to 1. So hit paste, And there it is, 0.6328, which is what we already got by doing it manually. Okay, so you can use this function in the calculator, if you want, or if you have a table, it's really pretty simple. Just make sure to include what it equals also. Okay. Now, if we want to make the probability at least 2 of the couple's 5 children have type O blood, in symbols that changes. It's the probability that x is greater than or equal to 2. We can compute this probability using the fact that to find a greater than, you would do 1 minus the probability that x is less than or equal to 1. All right? Anytime it's a greater than, to get that value, you take 1 and you subtract the probability that it's less than or equal to 1 number less. So we went from 2 down to 1. All right? And we've already found this value right here. Less than or equal to 1, we know is 0.6328. So I do 1 minus 0.6328. And I get 0.3672. Okay? So pay attention to the inequality. If it's a greater than, you have to subtract from 1 and you have to reduce that number right there. If it's a less than, you just can add up the boxes from the table, or you can use Binomial CDF. All right, let's try another example. Do people have a preference for the last thing they taste? Researchers at the University of Michigan designed a study to find out. The researchers gave 22 students 5 different Hershey Kisses: milk chocolate, dark chocolate, cream, caramel, and almond, in random order, and asked the student to rate each candy. Participants were not told how many kisses they would taste. However, when the 5th and final kiss was presented, participants were told that that would be their last one. Assume that the participants in the study don't have a special preference for the last thing they taste. That is, the probability of preferring the last kiss tasted is 0.2, 1 out of 5. So let x equal the number of participants who chose the last kiss. All right. Of the 22 students, 14 gave the final kiss the highest rating. Does this give convincing evidence that the participants have a preference for the last thing they tasted? Right? So we need to compute the probability that x is greater than or equal to 14 with our calculator. All right? So this is a bin situation. Either they remember the last thing, they had the preference for the last thing they taste or not. Each individual is independent of one another. There's 22 students in our trial, and the probability of a success that they gave us in the problem we're assuming is 0.2. Okay, n is 22. So remember, if it's a greater than, I have to do 1 minus, and then I find the probability that, that x is less than or equal to 13, right? So in my calculator, I'm going to do it this way. I'm going to do 1 minus, and I'm going to go in and I'm going to do binomial CDF, and it's going to ask me how many trials were there. There are 22 trials. What is the p-value? It's 0.20. And then what is my x value I'm interested in? Well, that comes from right here. That's 13. Okay? So I can put it in the calculator just exactly like that. Watch this. So I can do 1 minus second vars to get to binomial CDF. Number of trials is 22. The p-value is 0.2. And the x value was 13. So notice it did that. Now, be very careful. This says 1.01 times 10 to the negative 5. Okay, 10 to the negative 5 means that there's 4 zeros in front of that 1. So what does that mean? That means it goes 1, 2, 3, 4, 1. That's the answer here. Okay. So then the second question says, does this give convincing evidence that the participants have a preference for the last thing they tasted? Now, if you recall, we talked about statistical significance long ago. Convincing evidence means that it's going to be less than or equal to 0.05. Well, our answer is very much lower than that, right? So we would say because 0.00001 is less than 0.05, that's our proof, we have convincing evidence participants have a preference for the last thing they take. All right, that makes some sense, and we'll do some more examples when we get into class.